Chapter 11. Okay, this is slope deflection equations. So it's the indeterminate structure analysis actually separated into two groups. The first group is called force methods that we cover in Chapter 10. Now, basically, we talk about two methods. One is called compatibility approach. The other is the energy-based approach, include least work principle, Castigliano theories, and virtual principles. So basically, two approaches for force methods. And we just made a comments saying that because you go for the force, the redundant force, so the degree of redundant force then dictate how many equations you need. And we just say that most of the structures has a high degree of indeterminacy. So that's why it's getting more and more difficult to solve very complicated structure. Now, on the other hand, the other categories of methods called displacement methods, which use the displacement as your so-called degrees of freedom. So previously, we used force, which is called redundancy or degrees of indeterminacies. Now, if we turn around and say that, why don't we look at the displacements or rotation angle and use them as a degrees of freedoms, and then try to resolve the structures from that angle? Can that be done? So those kind of methods are called displacement methods. So they choose degrees of freedoms, which is the deformations, displacement, rotation angle, and then go through some sort of procedures to do that. Okay, so what is deformations? Deformation include displacement and rotation angles. So we need to define more clearly what do I mean by degrees of freedoms. So there are a few terminology here. The first is node. Node means that we have seen this. Node means the locations. Node. So node A and node B. What is element or what is members? Members. Members means like between two nodes. That's called one member. So this is of course artificial. This is not like, like the truth. This is artificially defined. So for instance, I can call this node A, call this node B, and this is one member. Or I can call this node A, this node B, and here's node C. Then it becomes two members, AC, CB. So this is artificial defined. Hello? I don't want you to, by the time you realize you already missed it. Because concept, again, maybe 10 minutes or 5 minutes, that's it. And if you miss that, no matter how much effort you put in, you will not be able to understand. All right, so node and elements or members, they are kind of artificially defined. But once you defined, then you can define degrees of freedoms. So degrees of freedoms include two types. One is displacement. The other is rotation angle. So if you define this as one members, you can see that node A is a climb end. There's no displacement, no rotation angle. So no degree of freedoms there. No degree of freedom. Node B is simply supported, a roller supported. So it cannot displate, but it can rotate. So the degree of freedom that you can get from this point is rotation angle B. So that's when you define one member. So if you define two members, this is one member, this is another member, then your degree of freedom is 1, rotation angle at B, as well as displacements at C, and rotation angle at C. All right, so you can see that For the same structure, defined differently, you get a different number of degrees of freedoms. So this is 1 degree of freedoms, and this is 3 degrees of freedoms. OK, so if that is the case, we can look at these structures and then define the degrees of freedoms now. So here is a hinge roller, or hinge. And loading is here. And you decided to model this as node A, node B, and node C. And this is 1 element. This is 2nd element. And you identify degrees of freedoms. So you know point A, the node A is going to be able to rotate. Point B also can rotate but cannot display. So both of them are restricted from displacement but allows to rotate in terms of rotations. So point C is a free end, so it's allowed to deflect as well as rotate. So as a conclusion, if you model your structures like that, then you're going to have 1 degree, 2 degrees, 3, 4. 4 degrees of freedom. Now, look at this frame. So you model this as a node, node, and node, and node there. So you have 1, 2, 3 members. And you plot the deformation shape of the structures under a horizontal force. Then you identify there will be no degrees of freedom at node A because it cannot display, it cannot rotate. Here, node B, it can display, it can rotate. So you got 2 degrees of freedom there. Node C, also you have 2 degrees because you can display and rotate. So you have 2 degrees. Node D, you don't have any degrees of freedoms. So there are 2 degrees here and 2 degrees there. So in total, you have 4 degrees of freedoms. But if you consider that this is so-called actually inextensible, which is an assumption that we commonly adopt for structure analysis, for frame structure, we always assume that it's actually inextensible, so it cannot contract, it cannot elongate it. So the deformation, the translations of B will be equal to translation of C. So delta B equal to delta C. So that kind of eliminated 1 degrees of freedoms. So as a result, this structure has 3 degrees of freedoms. So this is trying to define degrees of freedoms. So next, we need to set up the equations that we can use now. We are trying to use the degree of freedoms as our like unknown. So we go there and then try to find a solution that we're looking for and then come out with the forces. All right, so we need to set up the relationship between degrees of freedom that we just defined and the forces that act on the structures. So take a look at this simply supported beam under loading, and then it will deflect. So I want to take a small segment out and then do analysis. I want to take this segment out and then try to relate degrees of freedoms to all the forces that act on the small segments. So here is a segment. So before deformations and after deformations. So my objective is trying to relate the degrees of freedoms of this segment to the external force. So how much force apply and how much it deflect? How do they connect to each other? So you know that this is internal cross sections. So each cross section should have 3 forces acting on it, 3 pair of forces acting on it: bending moment, shear force, and axial force. Now, axial force for beam and frame, we can ignore the axial force. Shear force, temporarily, we can ignore temporarily. Later, we need to come back. So we just put down the bending moment there. This is the internal bending moment acting at these cross sections. So there's another bending moment that acting at this cross-section. Now, because of the nature of these methods, we need to define the sign conventions of the bending moments differently as before. So in the last two chapters, the bending moments are defined differently as compared to before. So please be careful. Also, my definition is different from the textbook definitions. This definition is more user-friendly, I think, than the textbook definitions. So I'm going to define, for these two chapters only, the bending moment as positive if they are doing counterclockwise. If they are going counterclockwise direction, I define them as positive. All right? Doesn't matter whether it's on the left-hand side or the right-hand side. As long as I see a counterclockwise moment, I call them positive. If this is a clockwise moment, I call them negative. OK, so far it's still preparations. So this is what I want to do. I want to relate the end moments to the degrees of freedoms that I see at point A and point B. I want to relate this to the degrees of freedoms at A and B. OK, so what are the degrees of freedom at A and B? Well, later on, I'll show you. So this case actually can be considered as a superposition of two cases. First case is I want to relate this to degrees of freedoms. And of course, all of these are caused by the external force. So the whole thing here can be considered as a superposition of two cases. One is I deform the structure into such a configurations and then estimate how much moment is there to maintain such a configurations without any force, right? So imagine that these are the two external forces. I apply some to the segments and then deform the segments. And I want to know what is the relationship between this and degrees of freedoms. And the second thing is, without further deform the segments, I apply the external force. And there will be forces at the cross-sections to resist such an external force. All right, so the claim is this. This scenario is equal to the superpositions of this plus that. Right? So this plus that equal to that. OK? So we can solve them separately. So that's a complete. So this case is a real case, can be considered as a superpositions of two scenarios. One scenario is, what is the moment required to generate such a configurations? The second is, what is the moment required to resist such external loads without further deforming the structure? Now, this case is easy. This case, we don't bother. We call this fixed end moment because it's not further deforming the structure. So we can consider this as like a climb beams and under external force. What is the reactions of the climb beam? So we call this fixed end moment, or FEM for short, fixed end moment. And we expect to get this solution from the table in the textbook. So all the fixed end moments should be able to be obtained from the table in the textbook. So we don't need to worry about that. So now we need to worry about this. If we can solve this, then superimpose, then we got that solution. So here, we want to answer these questions. So there will be degrees of freedoms at node A, degrees of freedom at node B. And I want to know the relationship between degrees of freedoms at A and B with the end moments at A and B without external force. So what are the degrees of freedoms? Degrees of freedoms is theta A, theta B, and the displacements of A and B. Displacement of A and B. But instead of looking at displacement of A and B, we look at the relative displacements. So we look at the relative displacements called delta. So the length of the span is L, so delta over L turns out to be the rigid body rotations called 5AB. So that's the geometry of the deformed configurations. So you have rotation angle, and you have rigid body rotation angle, which is kind of reflecting the relative displacement between A and B. So we want to connect these two end moments to all the degrees of freedom that I shown on the board. So how do we get that? So we want to set up the relationship between these two sets of parameters. So we do this. We look for a simply supported beam, apply an end moments there, M1. Calculate rotation angle here, rotation angle there. You can get that through the 5 methods that I mentioned. You can do direct integrations. You can do moment area. You can do conjugate beams. You can do Castigliano theories, virtual principles. Total of 5 methods you can use to find the rotation angles. OK, so the solution is here. Here's the solutions. And then you can set up the second relationship. So you come over to the other side and apply another moment there. Again, you can use one of the 5 methods to find out the rotation angle, rotation angles. So you can set up the second set of equations. Superpositions give you this. M1 and M2, superpositions of these two cases. So this angle plus that angle equal to this angle plus that angle equal to that angle. So you can combine and then come up with these equations. So theta 1 is theta 1 minus theta 1, 2. And theta 2 is theta 2 minus theta 2, 1. So the equation goes like that. Then you can rearrange here. M1 equal to that, M2 equal to that. So you see that we have connected M1, M2 to theta 1, theta 2, like that. So it's getting close to that, getting close to that. You see that? OK. So one more step, and we are done. Here. All you need to do is to tilt the whole structure, move the whole structure rigid bodily. From this position, you tilt up. Give it a rotation angle, rigid body rotation angle of 5AB, and then you end up with a case like this. So when you do rigid body rotations, it doesn't change anything, except that you need to redefine all the angles. So you can still use the 2 equations. You can still use the 2 equations. Because all I'm doing here, these 2 cases, I'm just tilting this point up by a rigid body rotation angle of 5AB. And that's it. So when you do that, it doesn't change anything, except you need to redefine all the parameters. So previously, theta 1 is here, but we are not interested in theta 1. We are interested in this rotation angle called theta A. This is the reference, right? We're always referring from the horizontal plane. So this is theta A. So we need to relate theta 1 to theta A. So theta A is equal to theta 1 plus 5AB. So or theta 1 is theta A minus 5AB. So you substitute in here, theta 1 equal to theta A minus 5AB. So similarly, theta 2 is equal to theta B minus 5AB. You substitute in here. So that's it. You don't need to do anything else, just substituting. So after that, you get this equation, just substituting the relationship. OK, so this is what I just said. And then you simplify it, end up with equations like that. So M1 equal to 2EI over L, 2 theta A plus 1 theta B minus 3 times 5AB. OK. M2, 2EI over L, 1 theta A plus 2 theta B minus 3 times 5AB. So you see, we are relating all the geometry here, the degrees of freedom there, to the end moments. Cool? OK, we're almost done. So that is the equations. That is a set of equations that we're looking for. Cool? So here we go. We start out with these conditions. We ask ourselves these questions. Can we set up degrees of freedoms, relate the degrees of freedom to the internal forces? So we go through some sort of derivations and successfully find out this relationship that accounts for these conditions. This is how much bending moment is required to bend the structures into producing such deformations. Now, we say that this case is a superposition of that plus this so-called fixed end moment that we expect to get from the table. So this is just coming out from the lookup table. So you are going to get it from the claim beams under set of external force. What is the moments produced at the claim ends? So that's called fixed end moment. All right, superimposed. Here we go. This one add up with that one. This one add up with that one. So here is a conclusion. And this is all called slope deflection equations. This is the slope deflection equations. This is the only equations. Or this set of equations is the only set of equations that you need to know, you need to understand and memorize for Chapter 11. And later in Chapter 12, we are going to derive moment distribution based on this set of equations. So this is a very important set of equations for Chapter 11 and 12. I wish I can make it more clear to you, but this chapter is a little bit difficult to derive because it's landed on a few concepts, superpositions, and those kind of geometry relationships. So it's landed on a few concepts. It's hard to comprehend. But this is maybe the best I can do. Half an hour, 20 minutes. But if you read, I bet, if you read the textbook, it takes you half a day. you won't be able to understand what the textbook is saying. Okay, you see, that's the end of our derivations. Now, for the rest of the time, we actually have 4 lectures devoted to this chapter. I will just illustrate these 2 equations through examples. All right? So the most important thing is these equations. And the rest is just illustrations. Now, basically, there's only one equation, if you can see it very clearly. If you are a very logical person, there's only one equation. Oh, also, please note that MAB, the subindex, MAB and MBA, they are not equal. MAB, MBA, they are not equal. So please be careful. And please be careful that we are going to follow these sign conventions. The moments that I define here will be positive if they are going counterclockwise. If they do clockwise, then it will be negative. But when you go to plotting the moment diagrams, of course, you should follow the definitions of the moment diagrams, right? You should plot it at a tensile side, or you follow some sort of coordinate definitions. OK. So fixed end moment AB will not be the same, will not necessarily be the same as fixed end moment BA. They are 2 different quantities. So be careful. They are 2 different quantities there. OK, so examples. So I just want to get the equations on the board again so that everybody knows what we need to do. All right, so not only the bending moment is defined as positive counterclockwise, but also the rotation angle is defined as positive counterclockwise. Right, so MAB, MBA are the end moments. Rotation angle is defining from the original configurations. This is the original configurations. So original configurations defined rotation angle theta A. This is positive. This is counterclockwise. Rotation angle B defined from the reference. This is the reference. So this is also positive rotation angle. And this is so-called rigid body rotation angle, 5 AB. Also positive counterclockwise. They should have another one called rigid body rotation angle, BA. BA, rigid body rotation angle BA is exactly the same as 5AB because this is rigid body, but not necessarily theta A and theta B. Theta A, theta B in general should be different. But rigid body rotation angles, because they are rigid body, so they should be the same. Okay. All right, so just now we derived two equations. So let me show you what are the two equations. Let me show you that I can memorize this myself. If I can do it, you can do it. Okay, that's the first equations. Second equations. All right, I can remember. Now, to be precise, EI is AB, L is AB. That's just to be precise, right? You need to know. Because this is coming from this component. So component have EI, EIAB, and L has a LAB. So just to be precise, should be like that. So this is more like an implicit you should know. Okay, so fixed end moment, let me just say that fixed end moment is referring to this. So this is the fixed end moment. Okay, so from table. No need to calculate, just from table. And I say that basically there's only one equation. You don't need to worry about the two equations. Let me show you the one equation. It's M I J 2 E I L 2 times theta I, 1 times theta j, 3 times rigid body rotation angle, and then fixed end moment ij. And that's it. So this is the slope deflection equations. So you put I equal to A, J equal to B, then you have the first equation. You put I equal to B, J equal to A, then you have the second equation. So the first index have 2 times rotation angle in it, right? While the second index have 1 times rotation angle. All right, so fixed end moment follow identical sequence. So that's the equations. So you don't need to memorize 2 equations. Just memorize 1. So let's use that equation to solve problems. Remember this. The needs of displacement method is coming out because you want to solve for a little bit more complicated structures, higher degrees of indeterminacies. Okay, but for teaching purpose, I always have to start with something simple, right? I cannot just give you a very complicated structures to begin. So let's start with this. Okay, here is a clamp and roller support on the other end. There's a midpoint load of P. EI is a constant. EI is a constant. So I want to analyze these structures using slope deflection equations. So go through the procedures. First, you need to define node elements or node members, and then define and find out degrees of freedoms. So I call this node A, and I call this node B. So the degrees of freedoms here will be equal to 0. So theta A is equal to 0. Displacement equal to 0, of course. B, theta B is not equal to 0, but displacement is equal to 0. So you can imagine the deflection goes like this. You can imagine it's not very good illustration. Okay, so that's the deflections. Theta A equal to 0, theta B not equal to 0. How about the rigid body rotation angle? So what is a rigid body rotation angle? So you connect the deformed shapes. You connect the ends of the deformed shapes. And then this is called rigid body rotation angle. So you connect this point and that point. So this is the deformed shaped. And you know that the rigid body rotation angle is equal to 0. So this is equal to 0. Okay, so we are ready to go here. MAB, MBA. So you write down MAB 2EI. L is the length of the members. 2 times theta A. Theta A is equal to 0. 1 times theta B. Theta B is not equal to 0. Rigid body rotations is equal to 0. So that's it. Nothing else. And then fixed end moments. Okay, that's MAB. MBA, 2EI over L. 2 times theta B. 1 times theta A equal to 0. Rigid body rotation equal to 0. That's it. Now you need to go to the textbook, fixed end moment table. You go to find this fixed end moment, both end fixed, and concentrated force in the midspan. So from the textbook, you will find the end moments to be PL over 8. So this is fixed end moment AB. This is fixed end moment BA, but this is clockwise, so it should be negative. All right, so far so good. We just utilize the definitions, plug it in. Any questions? Okay. Sam, you have any question? All right. No questions? Now, this is a clamp in. There's a moment, and you don't know how much moment is. There's a roller support. This is moment free. So this moment should be equal to 0, isn't it? Moment free. So you set this equal to 0. Guess what? You can find theta b. So you find theta b. Now, after you find theta b, you take that, substitute in here, you find MAB. All right, let me repeat again. You look at the boundary conditions. This is moment free, so you set that equal to moment free. The only unknown is theta b. You find theta b. You take theta b, substitute back in here, you get this value, which is MAB. Cool? So this is what we found. So let me just summarize what we have found. So we found out that this MAB is this there, and this is 3/16 PL. Moment there is equal to 0, of course. We know this rotation angles now. This rotation angle is theta b. So that's PL squared. 32 EI. Okay, now can you solve for the rest of the forces? So you come over here, take moment equilibriums, then you can find out this force. You come over here, take moment equilibrium. Why do you come over here? Anybody know? Huh? So there's a force there. Yeah, there's a force there. If you don't come over here, you take anywhere, then that force has to contribute to your moment calculations. So that's why you come over here, you eliminate this, and the only unknown is here. So you do moment equilibriums, you get that force. And you do force equilibriums, you get this force. Will that be sufficient for you to draw the shear force bending moment diagrams now? Yes, that's it. You solve your structure. Not only you solve your structures, but you also pick up the rotation angle on the wave. Isn't that nice? You see, you're not only solving the force, but you also solve the rotation angle. So the reason why it's called displacement methods is because they use this as a tool. They use the deformation as a tool. So you need to find deformation first before you get into force. So that's why it's called deformation method or displacement methods. OK, so just make it complete. I want to just show you the shear force diagrams and bending moment diagrams. So shear force diagram is like this. So that's the shear force diagrams. And the bending moment diagrams. I will ask you to plot at the tensile side. So tensile side. So this is a tensile side bending moment diagrams. OK, so that's it. It's quite good illustrations of what we put down on the board. This is the only equations I ask you to memorize. All right, any questions about this? If not, let's. I don't think I have enough time to get into the second examples. So, do you have any questions about this approach or this derivations? Is there any part of the derivations that you don't quite clear about? Huh? OK. Is MAB, good question, MAB, MBA, are they external or internal? Depends. Thank you. I won't miss, right? Depends. Let me show you what I mean. So you actually need more example to clear up the ideas. So the second example I'm going to give you next is this. It's getting more complicated. All right, something like this. So just now, there's an excellent questions. MAB or MBA, are they internal or external? And I say both. All right, depends. It's because depends on where those members are, moment are. So I'm sorry, where those moments are. Now, for instance, if I choose this as A, B, C, and I set up, and I call this M, AB, MBA, and this is MBC. This is MCB. So what do you think? Which ones are external? Which ones are internal? This is external, n moments. This is external. These are internals. So that's why I say depends. I cannot say it for sure. Okay. Any other questions? Yes. Are they the same? That's another good question. Are they the same? Again, depends. Depends on what? Depends on whether you have. What happens is this. Action, reactions. Okay? Action, reactions, action, reactions. So is this equal to that? For this case, yes. But if I apply a moment there, then it's not. Right? If I apply a moment there, then it's not. Okay? Also, they sum up to be equal to 0, so they should have a negative sign. They sum up to be equal to 0. So it depends. Okay. Any other questions? No matter what your question is, my answer is always depends. So, all right. Any other questions? If not, all right. See you next week.